is you cannot say pick as high as a value as you can. I know you can pick the highest value, but what is controlling is the cross-sectional area. So you have to focus on both the cross-sectional area. Now is where we do optimization, right, Eugene? So you have to focus on the cross-sectional area and also the SM value. Any idea why cross-sectional area, anyone? Why do we have to focus on the cross-sectional area also? Anyone? Because of cost. It's all about cha-ching. It's all about money. The bigger the cross-sectional area means the heavier the steel. The heavier the steel means more money. Okay. So let's look at the potential contender. Okay. So you can use S460. Okay, because it's 1690. Or you can also use 98.2 S510 98.2, which is at 1950, which is better. This is better, isn't it? Look at it, it's higher, right? Or you can, if you want, you can also look at 119 S610. So based on this three, so I'm going to write this three out. So you can use the S610 by 119. The area is 15200. Okay, and the S value is 2870. The other one you use is S510 by 98.2. Okay, and then this is only 12500. And then this is 19 is at 195. Wait, it's at 1950. Or you can select S460 by 104. Area is 13200. Okay, and then this is 1690. Okay, so we will always pick this one, lowest cost, lowest area, lowest cost. Okay, so I think this is very useful for its application now, right? It's very useful for more for civil engineers, but even those of you who are in manufacturing, this is also useful for you. Okay, so now you can select. Now, if you have combined loading, okay, then you have to use your principal stresses. Okay, then everything is go back to how I taught you in the past 2 weeks. Okay, right. So the next thing that we are going to do is we are going to look into another way of finding shear force and bending moment equation, and is using the integration method. Okay, so integration method, and I'll show you the integration method. Why is it more powerful? Okay, so the next one is integration method. Two. Okay. So I want to write up. I'm not going to derive the relationship, okay, but I'll write up the relationship. Okay, as I said, I'm going to. So the first relationship is when we have dv over dx, this is equal to minus omega. Okay. So once you have dv over dx, you integrate once. That's why you call the integration method. Okay. Now this is v as a function, omega as a function. It's distributed load. Okay. So you have V as a function of X. You integrate once, first time. Okay. So you have minus omega as a function of X dx. Because we don't have the limits, right? You have to have C1. Okay. And this expression is equal to dm by dx. Okay. And then when you integrate the second time, right? You have moment. Now you have moment as a function of x. You integrate twice. Plus by C1x plus by C2. Okay. So this is known as the integration method. Okay. Key thing to take note that this is minus. Okay. And C1 and C2 are determined from boundary condition. Okay, from boundary condition. So that's why when I started this class, right, for today, I taught your boundary condition, yes or no? Right, I taught boundary condition over here, right? What are the boundary condition? Okay, so let's look at one example. Let's if I have time, I will do two examples. Okay, let's look at one first. Okay, I think I'll do two example. Okay, I might go until like 12:15. Okay, maybe the second example I might not be able to complete it, but I want to show you how useful this technique is. Okay, so now we're going to have a cantilever beam. Okay, example number 2. And I think some of you might fall in love with this technique. Okay, but you have to be careful. Mathematically, you have to be very strong. And most of you have good grades for your math when you come to this class. I know that. Yeah. So we have a beam. Okay. So as I said, now this is cantilever beam. Yeah, we have cantilever. Then we have a distributed load, a gradient distributed load. Okay. A gradient distributed load. And this is at 6,000 Newton per meter. And now this is at 18,000. Okay. And then we have a distance from here to here. This distance is 6 meters. Point A and point B. So we want to find the shear force and bending moment equations and the diagrams. Okay. Now there are two ways of doing this. Okay. One is using integration method. The other way is doing superpositioning. Okay. I will not teach superpositioning. Okay. But I'll tell you what it is later on. Now, why this technique why we use integration method is easier is because of this reason. Okay, so if we were to form the free body diagram, right? If we were to form the free body diagram, right? So we will have, okay, we know that there is a, if we draw a transformation, We know that there is a force up here, By. We know that we have a counter moment NB, right? Now, we are aware there is a equivalent load. Okay? But can anyone tell me what is this distance? Anyone? I will tell you this. This is not equal to L over 3. Okay? Why it's not L over 3? Because only if it's a triangular load, right? Then it is what? L over 3. Or if it is a rectangular load or constant evenly distributed, we know that this is what? L over 2. But for this case, it's not. It's not a triangle, nor it's a combination of both. Okay. So that's why there's another technique. It's called superpositioning. You isolate the triangle and you isolate the evenly distributed load, and you just add them. Okay. More steps. Right. Azam, I know that you can get this in books. No dispute about it. Okay. Can you get this from books? Okay, can you have this expression over here? The powerful of this technique is this. What if I have a distributed load that looks like this? And this is equal to omega as a function of x. And this is x6 plus by 3x5 plus by blah, 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 blah. Can you find me the expression, please, Azam? Where is the equivalent load distributed? There you go. Azam has just helped me in this course. I think I have to give him a beer when I see him the next time, right? So that's where you cannot use this expression. You cannot use if you have a curve of distributed load, which is in a bridge, you do. Okay, there's no way you can use standard method. You have to apply what? Integration method. Okay, so I give you a load like this because it's simple. Okay, it's simple to write out the expression. Okay. Now, some of you might ask me, then if we have a load like this, how do we find the omega x, right? You use curve fitting. Okay, you plot everything on Excel, okay, and then you generate the equation. Simple stuff, okay. I think some companies cannot afford very expensive softwares, okay. They just use simple software like this, okay. So you have that expression over there, okay. So how do we do it? Okay, so fundamentally, how do we do it? Okay, so you need to know your boundary condition, right? So this is V and M, theta Y. Okay, V and M, theta Y. Okay. So we know V over here is equal to 0. Moment over here is equal to 0. Y is equal to 0. That's all we need to know. Or that's all we know. Okay. So the first thing we have to do is we have to find omega as a function of x. So omega as a function of x is the equation of the distributed load. So I'm going to draw I'm going to draw a different graph now. I'm going to draw a different graph. So now the graph that I'm going to draw, okay. So this is x, this is omega. Okay, so one side is 6,000, the other side is 18,000. Okay, so this is at it's 6,000, 18,000, and the distance from